good. So, I believe we started problem 3. And we just have to finish that and then go to problem 2. Okay, so the insurance company found that on average over a period of 10 years, 23% of drivers in a certain zip code had an accident. Who had an accident 1 year, had an accident the following year, so accident, no accident in the year. There are 2 states, we drew these last time. Okay, so 23% of people who had an accident 1 year also had an accident the following year. That means that they're 23.23. Which means they went from a state of accident to no accident with, what's that, 77? And 11% not involved in an accident had an accident the following year. So that was 11, which makes this 0.89. Yeah, draw the transition diagram, and that was that. Then we wanted to find the transition probability. I believe we did this already. I'm just recreating it. So here's 1, here's 2, here's 1, here's 2. 1 goes to 1 with 0.23, 1 goes to 2 with 0.77, the rows should add up to 1. 2 goes to 1 with 0.11, 2 goes to 2 with 0.89. So that was B. This was A. I think that's where we got to. And C. Okay, 5% of drivers had an accident. What's the probability that a randomly selected driver will have an accident the next year? How do you do that? So what is that telling us? 5% of drivers had an accident in 1 year. What is that? Yeah?
Don't you multiply S and P?
Oh, but what is S?
0.05 and 0.95 and original.
So telling us 5% had an accident, meaning there's 5% of people who were in state 1, and consequently 95% of people were in state 2, not having an accident. So that first phrase there tells us that, gives us an initial state matrix. And so S2 is the state in the following year. That's going to be S1 times P, 0.05, 0.95 times this guy, 0.23, 0.77, 0.11, 0.89, and S has to be on the left because you know how matrix multiplication works. This is a 1 by 2, that is a 2 by 2, so these must match up. The result is going to be a 1 by 2. Which is going to be, in this case, 0.05 times 0.23 plus 0.95 times 0.11. And 0.05 times 0.77 plus 0.95 times 0.89. And what were these? So, to answer this question, 5% had an accident 1 year. What's the probability that someone is going to have an accident the following year? would you answer that? Will. Will is a strong word. Have an accident involving you. So, just look at all the people who are in state 1 in the second state matrix. And I think the question also says the year after. And that's pretty much asking for state 3. Well, that's just going to be state 2. So we take that as the initial and multiply by E. So 2 years down the road, how many people will be in a state of accident? We're going to have 0.116, 0.23, plus 0.884, 0.11, 0.116, 0.23, plus 0.884, 0.89. Someone's trying to figure out how to get out of here. What's the quickest way to get out of here? Coincidentally, our last example is going to be one about traveling.
Oh, man.
Turns out Markov chains help us figure out good traffic routes. What is this? Right, calculate that. And then we'll know the answer to that box. Point 1, 2, 3. 1, 2, what? Okay, so 12.4% will have an accident fault. So I'm an insurance company insuring people in this zip code. A random person comes, signs up to have an insurance policy with me. They give me their address, and I realize that they're in this zip code. I would assume there's an 11.6% chance this guy's going to have an accident in the next year, and a 12.4% chance he's going to have an accident the year after that. To find the average cost of each accident for people in this zip code, I can tell you how much money this dude is going to cost me, and then I can choose, of course, with other factors taken into account, but this will be one of them. I can choose how much to charge him for an insurance policy. Because I kind of know what are the chances he's going to have an accident, and I can know what is the average cost of an accident. So I can kind of use that to predict how much money I'll have to pay out on average in this area. So that's pretty cool. And one of many uses of Markov chains. Probably even the people who work in the insurance company punching your data into a computer don't really understand that this is what's going on in the background, but this is one of many of the wheels that are turning in the background, trying to figure things out. Problem 2. Now this one's a little bit more complicated than it might first appear, because you see that there are 2 players, so you might assume there are 2 states, but there are actually 4 states in this one. So 2 players, player A and player B, are playing a special type of basketball shootout game. Player A goes first, And we know that A makes the shot 60% of the time, B makes the shot 80% of the time. So B is the better shooter on average. Here are the rules. If A makes the shot, he can go again, right? Because he's the worst player, I guess. Player B is just giving him a chance. Otherwise, B goes. If B makes the shot, he allows A to go the next round. Otherwise, he goes again. Find the initial state matrix for this game after the first round. So here are the states that I would put here. Because each player can have 2 states, so there are actually 4 states here. Let's call one A makes it. Or A can miss it. 3, B makes it. Or B misses. So each player can be in 2 states, so this is a 4-state situation. You can be in the situation where you're the winner going into the next round, or you're the loser going into the next round, and both players A and B have that option. So there are actually 4 states here. So, the initial state, if I had to do 1, 2, 3, 4, so player A goes first, we are told that right here. So if player A goes first, what is the situation after the first round? Well, there's a 60% chance that player A is going to make the shot. And if he makes the shot, he goes again. So it'll be in this. So if A misses the shot, so we're in state 2, we, according to the rules, B is gonna go. So how do you fill out the rest of this? Like, you guys know why I'm here trying to figure this out. How do you fill in the rest of that?
I would just go 1, 2, 3, 4, first one.
So 1 is A makes it, A misses, B makes it, B misses.
What's it, 0.4? So
Come again?
it's 0.4.
0.4, 0.8.
Yeah.
Come again?
And that goes 0.4. And then it's 0.8. And then it's
No. Why not?
Rows have to sum to 1.
They have to add up to 1, so that can't be the right answer.
I think the structure
Would just be different. 30.2.
Well, what does this actually say?
There's conditional probabilities in here. He only shoots if they misses. Right?
Yeah. The first one, yeah.
Yeah.
So A goes first. What is the probability that he's going to make the shot? 0.6, which means he would be, who would play if he makes the shot? He'd go again. And then the probability he makes it is going to be 0.6. The probability he misses it is going to be 0.4. Now, B would not get to play in this situation. That is going to be 0 and 0. So that's the initial state. If you look at B, why is this? Find the transition probabilities and transition matrix. I kind of just do the matrix because you automatically find the transition probabilities by using the matrix. 1, 2, 3, 4, 1, 2. Let's make this a little wide. Okay. If we're in a situation of A making the shot, what is the probability that he's going to make the shot again? Well, 0.6. What if we're in a position of A makes the shot, meaning A is going again, what is probably he'll miss the shot? Well, 0.4. And if we're in the position where A wins, B doesn't actually get to play, so he will neither make nor miss the shot, so that's 0, 0. If we're in the position that A misses, that's what state 2 means, okay? What is the probability that he will make the next shot? Well, that probability would be 0, because if A misses, B gets to go, so A is not going to have any probability of making it. He's also not going to have any, it's not his turn. However, B will have the opportunity to actually make the shot with 0.8 or miss it with 0.2. Suppose we're in a situation where B makes the shot, right? So in the last round, B made the shot. What is probably that A is going to make the shot in the following round?
This is not shooting.
If B makes the shot, then A goes. So yeah, if 3 happens, A is actually the guy who's going to shoot, and he'll win with a probability of 0.6. If B had made the shot in the last round, A will get to go next, and he has a 0.4 chance of missing it. If B made the shot, it's A's turn, so he's not going to play, so 3 and 4 would be 0. If we are in a situation of 4, which means B misses, the rules say if B misses, he gets to go again. So if B misses, it's not going to be A's turn, and he'll have the chance to make the shot with these probabilities. So that would be the transition matrix here. So I just gave you this example to show you that it's possible to have zeros in your transition matrix. And I think we wanted to draw the diagram after, so let's draw that. 1, 2, 3, 4. 1 goes to 1 with 0.6. 1 goes to 2 with 0.4. 1 does not go to 3 or 4. 2 goes to 3. 2 goes to 3 with 0.8. 2 goes to 4 with 0.2. 3 goes to 1 with 0.6. 3 goes to 2 with 0.4. 3 doesn't go anywhere else. Okay. 4 goes to 3 with 0.8. And 4 goes to itself with 0.2. So that's the transition diagram. That's just an example of a bigger transition diagram. Now, I just want to set you up for some problems that we're going to have when you get back from break, look into the future. I'm going to tell you about some new types of Markov chains. Let's get through those. About the idea of an absorbing Markov chain. You know what's a regular Markov chain? We talked about that last time. What is an absorbing Markov chain definition? you have something called an absorbing state. This is a state that once you enter that state, you can't actually leave, i.e. the probability of mapping to itself. Is 1. You'll notice that none of these states in any of the previous examples were absorbing. This is a new kind of behavior here. Condition. Markov chain is called an absorbing chain. If 1, there's at least one absorbing state. And 2, it's possible to get from any non-absorbing state to an absorbing state. Let me give you some examples of that. So here, you'll notice 2 is an absorbing state. But the chain itself is not absorbing. Because it's not possible for me to go from one of the non-absorbing state to an absorbing state. The matrix for this is 1 goes to 1 with a third probability, 1 does not go to 2, 1 goes to 3, 2/3 probability, 2 only goes to itself. So you'll have a line where they're all zeros and a 1 in the guy mapping to itself, and 3 goes to 1 with a half probability, goes to itself with a half probability, and goes to 2 with 0 probability. So you end up with a matrix that looks like that. Now, the picture you can clearly see when it's an absorbing, you have an absorbing state and a non-absorbing chain, but the matrix probably is not going to clear. How can you look at a matrix and know? I'm going to tell you how you can look at know from the matrix. Here's another situation. You might notice here that 2 is again an absorbing state, and at the same time we have an absorbing chain. Because for all the non-absorbing states, it's possible for them to enter an absorbing state. So 2 is an absorbing state. And this is an absorbing chain. this guy is going to look like if you draw his transition matrix. 1 goes to 1 with a third, goes to 2 with a third, goes to 3 with a third. 2 goes to itself with probability 1. 3 goes to 1, 0 at the time. Goes to 2 at half of the time. Goes to itself at half of the time. So notice we can get from 1 to 2 or 3. We can get from 3 to 2. And once we actually get to 2, we can never actually leave 2. We'll just get these stuck there. These chains are important. They have many applications, and we kind of want to know when we're looking at one. Facts on observing chains. Which we'll put into practice next time. 1. The transition matrix. There's a form called standard form. And standard form means you can write it in the form you'll be able to rearrange the states so that you can write it in a form that looks like this. There's going to be an identity in the top right corner. Top left corner, there are going to be zeros over here. They're going to have 2 matrices over here. Call them R and Q. Where the Q is going to be the same size as I. And this I is the identity we're talking about. So I'm giving you an example. Add a big one written over here. Somewhere.
Wait, don't we have a midterm next time?
What?
Yeah, don't we have a test on Wednesday?
Test on.
We only have one fun.
Do we not have it?
I don't know. The test is on the last day of class. I don't know when is that.
Right.
We don't have another week, so we
On the
have-
syllabus it says next Wednesday the 4th.
Yeah,
Okay. All right. Yeah. Then yes.
but like,
Can we take it on Friday?
Yes, that's correct.
but like how?
What do you mean how? What do you mean how?
Wait,
Can
can
you
we
at
take,
least post like review sheets?
Yeah.
Oh yeah, yeah. I'll do the same thing like last time.
wait, can we do it on Friday so we can come to office hours?
Yeah.
About the review.
I'll do it like today or tomorrow. Which gives you like
No,
a
like,
They mean the
Could we
test.
take the test on that Friday so that we can come to your office hours about?
Do we have class on
Yeah.
that Friday?
Yeah.
Yeah.
No, why not?
Last 3 classes.
No, Friday is
No.
It's the sixth.
I mean, I think it's the last day of class, so if
Okay.
Friday's
Yeah,
last day of
we
class,
do
that's
that.
the test.
That's our
Okay.
Okay,
Yeah.
so
Wait, so
changing
it
it.
is the 6th now?
Yeah, it's on there.
So it's the 6th, yeah.
Alright.
Did the syllabus say something?
It says the 4th.
It's on 4, you said nothing.
So it's the 6th, like this is
Yeah, we're solidly going with this.
Yeah.
Wait, Jhevon, so are we going with the 6th? Is that?
Yes, yes,
So,
Oh, that makes it so much better. I just understood it.
yes.
I think it's on the 11th.
0, 1, 0.
It's on the syllabus, it's on the.
Point 3, point 4, point 1, 2. This is an absorbing chain since we can write it as, so you see see a matrix like that, a bunch of zeros, and you see some ones in there too, you might consider trying to rewrite it. So there's like state 1, state 2, state 3, state 4, 1, state 2, state 3, state 4. You can kind of shift the states around. Like you notice that 2 and 3 map to themselves, so let's do 2 and 3, 2 and 3, and then the other guys are 1 and 4, 1 and 4. 2 maps to itself and to no one else. 3 maps to itself and to no one else. And now 1 maps to 2 with probability 0.5. 1 maps to 3 with probability 0. 1 maps to itself with probability 0.5, these map to 0. 4 maps to 2 with probability 0.4. 4 maps to 3 with probability 0.1. 4 maps to 1 with probability 0.3. And 4 maps to itself with probability 0.2. Notice that I can kind of imagine this thing split into 4 sections, where that's going to be I. This here is my Q, which is the same size as I. And this here would be your R. And notice that I have all zeros in that top right corner. An absorbing chain will always look like that. 2 in an absorbing chain. As n goes off to infinity, p to the n will go towards. So the transition matrix is also going to be predictable how it's going to look. If you start from standard form. So if I took this matrix and keep multiplying by itself over and over and over and over and over for a really, really, really long time, it will start to look like this matrix. It's going to be an identity over here. There's going to be zeros over here. There's going to be all zeros over there. And here, we're going to have a product of 2 matrices, F times R, where the R is the guy from the lower left corner in the previous matrix, and your F is actually I minus Q inverse. And these would have the same size, so you can do that.
Is that negative infinity there? As n approaches negative?
No, just regular infinity. That's an arrow. I'll probably never ask you to find this form because this is too much. But you should know that you can actually restructure absorbing chains to look like that.
Wait, how?
We'll do next time.
Wait, Jhevon, how did you get this one?
Oh, you saw the matrix that I wrote down here?
Yeah.
I just saw all the guys that map to themselves, and I grouped them all on top. So 2 and 3 went to themselves. And so I grouped them all on top, and then I put everyone else below them, and it'll create an identity right here and zeros over there. So I just rearranged it 2, 3, 1, 4, 2, 3, 1, 4 instead of the 1, 2, 3.
And you can like arrange it.
Yeah, you can always arrange it to look like this, where there's an identity over here, and there's a matrix of the same size on this corner. And if you can't do that, it's not absorbed.
Is that considered a proof for like, show that this is an absorbing matrix and you reorder it that way?
For 1108, that counts as a proof, yeah. Like if I say, oh, show that this matrix is absorbing. If you can write it in that form, then I would say, okay.
Oh, so you can always rearrange it like that.
Yes.
And
And if it's not absorbing, you can't.
Okay.
Yeah, for now, that's all I want you to know. But I kind of wanted to end with a nice example here. Give you something to think about as you go off to Thanksgiving. About Markov Chains. So, we're going to do a little thought experiment. So, no real calculations. I mean, calculations were done, but I actually just did them at home because the thing is a huge matrix. So, consider this chain. A, B, C, D, E. Okay, A can go to B, B can go to A, B can go to C, C can go back to B, C can go to A, D can go to A, C can go to D, D can go to C, D goes into E. So imagine you have that chain. So here's the situation. Think of these as torus estimates. I don't know which one the person earlier was trying to map to, but so A, B, C, D, E, torus destinations, right? And the edges are paths, roads, whatever you want to call it. You can travel around. And so the direction is indicated. You can move from city A to city B. You can go back from B to A. You go from B to C. There's no direct way to go, say, from A to C. If you're in city A and you want to get to city C, you have to go to B, then C, etc. Right? So this might be something like plane routes, right? We only have flights going from A to B and B to C. There's no flights directly from A to C, things like that, right? So these are the paths that you can travel. E is absorbing, but we'll actually change this assumption. We make the assumption if E is entered, you can go to any other state with equal probability. Last assumption, there is an equal probability of going down any path. So the technical term for this is called a random walk. So I think Jack Bogle wrote a book called A Random Walk Down Wall Street. A lot of people think it was just talking about just walking. No, it's talking about this kind of thing. So a random walk means if you're in one location and you have paths leaving that location, you can choose any path with equal probability. So for example, let's actually do the matrix for this. A cannot go to A. What are the chances that A will go to B? 1. Can B go to A? B can also go to C. So that's a half here, 0 here, 0 here, 0. Right? C can go to, how many paths leaving C? 1, 2, 3. So it will have a third of a chance going to any of those. Third going to A, third going to B, third going to D, 0, 0. D, paths from D, they're also 3. There's a third probability it'll choose A, a third probability it will choose E, and a third probability it will choose C, but it can't go there and there. E, it's absorbing, but the assumption is it's not going to go to itself. If you end up in E, there will be equal chance that you can just randomly pick one other city. So this will be a quarter, 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 quarter. So all this.
Does that change the diagram, or are we just like?
Huh?
Wouldn't that like change the diagram so we lines?
Yeah, but there'd be lines connected everywhere like that.
Oh, okay.
But we just don't write it because
So
it can get confusing.
you use
Like when these things actually happen in reality, it just makes things confusing. We just assume one point can literally connect to every other point.
So if you don't draw like a circle to itself, you know, you can assume that it's going to every point.
Yes, that's how we kind of set it up. Here's something that you would notice. Well, you wouldn't notice, but I noticed because I plugged it into Wolfram Alpha. P to the 6 has only positive entries. This means, what does that mean for P, or the Markov chain?
There's a solid state matrix exists.
Right, it's regular, which means a stationary matrix exists for this random diagram that I just drew. In fact, I actually computed the guy again using Wolfram Alpha because the point is not to actually do the calculations, but for you to actually see this cool application. 44, 6 over 149.
No, that's on Wednesdays.
33 over 149. Let's get right into here.
If we did on the what?
This is 12 over 149. And this is 4 over 149. So now the question is, how can that matrix be interpreted? I want you to know.
I got a test.
I got a flight.
So basically this tells you in the long run, kind of where most people are going to end up, right? So you just throw a bunch of random people on this map. Let's say I throw 149 people on this map just randomly, right? And just have them randomly choose paths that they're going to go, cities they're going to travel between, right? It turns out that 44 of them will end up traveling to city A, 56 will go to B, 33 would C, etc. Right? So in other words, if someone were to ask me, what's the most popular city in this region? Well, it would be B, then A, then C, then D, then E. Right?
Yes.
I'll tell you the significance of that next.
Why, so you're gonna post the review packet though?
Yes. We're over time. Okay.